Hello, welcome to practice 4. We're going to look at some traditional classification methods. The term I use for is called traditional here. That means not neural networks. A lot of deep learning is focused on neural networks, deep learning, neural networks, and things like that. But these are non-neural networks classification methods that are also popular in a number of areas. So we're going to look at those. So let's take a look. So you can open up this work notebook either in Jupyter Notebooks or in Colab here, and let's look through this. So again, we're going to revisit the IRIS database, which we looked at earlier. So if you remember, the IRIS database has a set of characteristics for 3 types of irises here, and we're going to try to learn to classify those. So as normal, we're going to set up our tools in Python. So we're going to import our libraries we're going to need. We're going to then read the IRIS database from the from online here, from the GitHub link. Now, one note is that before we read in a modified IRIS database with some errors in it. Now we're reading just the original IRIS database, and so there shouldn't be any weird values or things like that. So it's already been cleaned up, so we don't need to do any of our data checking or cleaning techniques. And again, we can display the first couple iris flowers here. And again, we have 4 characteristics for each flower and then the identifying species here. Now, the first thing we're going to do is break the data up into an x and y values. X is generally a variable used for the input to our information. Y is our output of this. X is often capitalized, and one of the reasons is in math, when you have a matrix or multidimensional vector, you often capitalize it. Y is often lowercase, and that's because, again, we just have a single dimension. So again, this would be our x, our input, and this would be our y. But actually, it is just these 4 columns are the x, and this one column is our y here. So here we're just going to grab columns. This is an ID, which is not a column. It's a little different. And so we're going to grab from 0 through 4, not including 4 for this, and from 1 to 4. And that's just number 4 here. Now, another way to do this is you can actually specify the column names and grab those, and then just the name of the species and grab those. So this you can either grab by number or by name here. But one more thing we have to do is we're going to split this data. As we mentioned before when we were looking at our first model, we want to split the data into some training data and some test data. And we will train our model or set up our model using the training data and then evaluate it with the test data, but we will not adjust our model at all with the test data. So that's what we're going to do here. And so we're going to do our train test split here again with our X and our Y data. We're going to do 80% training and 20% testing in this example. So we'll use these variables X train and X test and Y train and Y test for this. So now we're going to look at a number of classifiers. This is a common supervised machine learning technique where we have distinct categories and data, and we want to learn from the data how to classify new data into one of those distinct categories. So we're going to look at 3: the KNearest Neighbor, support vector machines, and decision trees here. So the first one we're going to look at is KNearest Neighbor, also referred to as KNN here. Sorry. Okay. KNN. So let's just assume, to give you an idea, we have some fruit here, apples or oranges, and we measure some values here, maybe the smoothness of the fruit on one variable and then the amount of red color in the fruit in another variable. And then so we plot those out, and so here, and we have it all labeled. In this case, the red squares are apples and the oranges are here. So for example, we have an orange whose smoothness was measured at 3 and whose amount of red color was measured at 15 here. These are just made up data to illustrate some points here. So we can plot this out, and then we can look at if we have some new value, and that's shown as an X here. So we have some new value where we measured the smoothness at just under 5, and then the redness at what is this? Just under 19 here. And we want to know if that's an orange or an apple. So what we can do is look at just what the nearest value is. So measure the distance to every value here and just find this is the nearest. And we can just see that visually here. This is the nearest one. And so we would classify this as an orange by just measuring the nearest one. Okay. So that's what's called just the single nearest neighbor. But often you don't want to just do that because you might have some stray data around that makes this inaccurate here. So maybe you want to do more than that. So in this case, let's say we looked at 3 neighbors. So if we look at the distances to every fruit in our data set, we can calculate the 3 closest. And you can actually look at this visually. It would be this one, and this one. These are the 3 closest here. And then so with those 3 closest, we would then kind of have a vote. 2 of them would vote for apples and 1 would vote orange. So the apples would win. So then if with 3 nearest neighbors, we'd classify this as an apple because there's more apples and oranges here. So that's what we're kind of trying to do here. We use the Euclidean distance out of the fruit. So just straight line distance. That you can measure. Although this is often in multidimensional space, we're using only 2 dimensions here, but like in iris data, we're using 4 dimensions for that. And again, we can find the 3 nearest fruit and assume, and in this case, there would be an orange, an apple, and another apple. And then based on that, we classify that as an apple. But we could also do if we have lots of dots here, we could do the 5 nearest neighbors or 10 nearest neighbors or the 100 nearest neighbors for that. So your task is then to look at this, and we've already gone through this, but how would you classify it with what's the 1 nearest neighbor, 3 nearest neighbor, and 5 nearest neighbor? How would you classify the X here? And so we've just gone over that somewhat, but you have to do the 5 one, and then put your answers for all 1, 3, and 5 down here. Okay. So next we're going to do this actually in code. Here's the code for this, and this task 2 uses this code here. So we set up a KNearest Neighbor classifier. We import this from our sklearn library, and we have to specify how many neighbors. So right now we're using 5 neighbors here, and then we fit the model to the data. So we provide the X and the Y training data. And then once we fit the model, then we can score the model on the test data. So we give it the test data and see how well it performs here, how well it classifies, how accurate it is here. And then we're just printing off, we're saving that score, and then we're just printing this off, and that's what it is here. So with 5 neighbors, the score is 0.96, so 96% accurate. So this number will be some number between 0 and 1, and 1 being best, that we're 100% accurate in our prediction, our classification using of our test data here. So your job is to score with the iris data 1 neighbor, 2 neighbors, 5 neighbors, and everything. So again, you would go in here and just say, what happens if I change this to 1 neighbor, and you'd run this. And then your result is X train not defined because I forgot to run this code up here. Okay, run that. I usually would just do run all here when I open this up, but I'm trying to show it to you one by one. So I ran that. Now I'm going down here, and now I'll run this again. Okay. There, and the score is 0.93 with 1 neighbor. And again, try these different things. Yeah, here's some initial values to try. We put in the 5. You can now put in the 1, and you should run it again. When you run it, might be slightly different because again, it randomly chooses some of this stuff set up here. And particularly how you do set up the X the selection of the X test, X train and X test, and Y train and Y test is random values from that. So sometimes it's slightly different. Okay, and then do it with 50 neighbors, 100 neighbors, and then select some other ones. See if you can find what are some optimal values for the number of neighbors here. Now, there are some problems with the K-Nearest Neighbor algorithm. It's not the most efficient algorithm. It works well for small data sets, but for large data sets, it is very slow because every time you need a new data set, a new data item, you have to compare it to every item in your data set. So, like if we wanted to predict what movie you wanted, and we were like Netflix, and we have a database of 1 million movies out there, when we get a new movie in and want to see what it's similar, we'd have to compare it to maybe 1 million different movies. Or if we have users, if we have a new user and want to see if that user is similar to other users by some ratio, we might have 100 million users. So not only do you have that large data set, you have to keep it in memory and do your comparisons to everything. So it is only K-Nearest Neighbor is really only used for small data sets for this. So we'll look at some alternatives to that next. So one more thing before we go then task 3 is, what if we wanted to, we've trained our model, so you've trained it, you've got a very accurate prediction here. Now we want to use it. So what if we wanted to predict something? We measured a flower with a sepal length of 5.2 centimeters, a width of 3.3, and the petals were 1.4, and the width was 0.2 here. So we can use our model to make these predictions. We can just create an array with these values. It's very similar to just creating a, where's our data up here? A row of these values here, these 4 values. So we're basically creating a row of those values here. So in Python, we do that by saying bracket and then listing the values in that order. So we list them in this order here. And so we set this up. There's actually a parenthesis, a square bracket, the numbers, another square bracket, in parentheses. It just has to be that way because we can, just the way we want to do the predictions. We call our model and tell it to predict based on this, and it'll generate a prediction, and we can print it out, and it should print out the right species. So I want you to change this and make a prediction for a harder to predict flower, an iris, with these measurements. So set this up and change that, and we should see your prediction, see if it matches this. Okay, so now we're done with K-Nearest Neighbor. We can go on to support vector machine. This is a very popular machine learning format these days. So support vector machines allow you to classify data. What it basically tries to do is divide the data into chunks. There's a nice video that walks you through this, but there's also this text tutorial. Let me just bring that up. So here what we're looking at is data that's broken up into categories. Here we just have two-dimensional data, and we have 2 different categories, some red boxes here, some blue circles here, and we want to classify them, and they're separable, so we can draw a line between them, but there's actually quite a few different lines to draw. So one of the questions is, which is the best line to draw? And so what we'll try to do is find the optimal line that we have here, so that the distance between that line and all the data points is maximized. And so it's a technique that goes through and finds this line and how it works. Now this is 2-dimensional data, and so we just have a line, but this, if we have like 4-dimensional data, this is actually what's called a hyperplane instead. So this shows 3-dimensional data and then a plane going through here, dividing it, and then higher dimensions work the same. And again, there's just this support vector. These, the distance between the data points on the fringe here and the line, those are called support vectors. That's why this is called a support vector machine. It finds the best line to make those vectors the longest. And again, we're not going to go into how the math works for calculating this. It's well-known algorithm, and it's implemented in most libraries. Now, if you have a math background, the math is accessible out here, and you can go through this. But again, for this class, we're not going to go through this portion of it. And again, this is a nice video that also introduces that. Now, once you have that set up, The one we looked at just used straight lines, but there's another technique that uses curves. So rather than having straight lines, you can use, if this is for example your data, you can use these curved lines here to try to find the maximum. Now it doesn't always work. Again, there's often will be some points that won't fit, that will be misclassified here, but it tries to find a good curve for this. And there's a couple different, these are called kernels. One is the linear kernel, the most straightforward one we looked at first. This kind of curve is called a radial basis function curve. There are other ones, but these are the only two kernels we're going to look at. Now there's also a question related to the penalty that you have to pay if you misclassify some items. So here's a link to a Stack Overflow article here. Someone asked the question, what is this C parameter, the penalty parameter? There's an answer, but I actually like the second answer here, which shows, so if you have a bunch of points here and a bunch of other category points here, and you have one kind of strange point here, the question is that how do you position your line? If you don't have much penalty for classifying data wrong, then we'll use most of the other points to draw this line, and kind of ignore or have less penalty for this one bad point. If you have a large penalty, a large value for C, it's going to really try to draw this line so that it includes all the data correctly here, and try to position the line as best it can. So low C will ignore some extraneous data points. Large C will really try to get everything to fit perfectly as best it can. So it kind of shows that sort of idea. So your job is to run this. This is our code again. We just create a model, and we just call support vector machine, or controller here, SVC, and we can specify the C, our penalty, and the kernel. And again, if we want to use the RBF kernel, we just specify it this way. And again, we can specify different values of C here. So you should use one or the other. Now you notice this one, it has a pound sign in front of it, so it's commented out, it's being ignored. Anything with pound signs are ignored the rest of the line. So this is the one piece of code that's being run here, the linear kernel with a penalty value of 1, which is a standard value. Then we fit the data to the training set. That's where it finds the best line, and then we test it out with the test data and see how it scores. In this case, a linear kernel. Let's just run this. Is going to predict different values, and again, depending on what you have for your random numbers, you'll get different values here. Here I'm getting a really good value of 1.0. And again, but when you run this, you might have a different split with your data here. And then with that different split of data, I get a different number here, very close, but then slightly different. So what I want you to do is record a linear kernel with this, and this is the score I got just recently. Put that in. Run a different kernels here, RBF kernel with a C of 1, and then do at least 3 other combinations of scores, different kernels. Try to get some good results of this thing. The iris data is pretty easy to classify, so you should be able to get very large values hitting 1 easily with the support vector machines, which are actually very good classifiers. So the last classifier we're going to look at is called decision trees. And what that does is create kind of a whole if-then structure by looking at the data and breaking the data up into parts here. This is an example that's from the SK Learning documentation on decision trees, and what it does is say, well, I'm going to look at the data. First, you notice the petal length is so value. At some value, I can break the data into parts, and if it's above, or if the petal length is less than this value, I can then classify it as this, and vice versa. So it tries to determine this kind of characteristics, try to figure out how maybe an expert would classify this. Like expert might measure, well, if a petal, if any flower with a petal greater than this length would be this flower. Otherwise, we have to do another measurement. We'd have to then measure the petal width, and if a petal width is less, then we can classify it as possibly this flower, and then we have a whole bunch of measurements and decisions, kind of comparing the numbers until we do our predictions here.